Section: Introduction. In this section, we discuss the challenges faced as language model architectures grow larger, making pre-training more costly. To address this, many attempts have been made to create efficient optimizers to reduce these expenses. Despite these efforts, ADAM remains the most commonly used optimizer for training language models due to the belief that it generally performs better than other optimization algorithms. While some newly proposed optimizers have shown better performance than ADAM for specific architectures and tasks, there is no consensus in the literature on which optimizer is superior. Our work is the first to compare these optimizers in the context of masked language modeling at a single model scale. We conducted a thorough analysis of training autoregressive language models using various optimizers, hyperparameters, architectures, and scales. We not only focused on achieving optimal performance but also emphasized the importance of stability in performance concerning hyperparameter choices, especially as the scale increases. Previous studies have explored the stability of learning rates in ADAM, but we extended this investigation to include the stability of multiple optimizers across different hyperparameter choices. Surprisingly, we found that newer optimizers like Lion and Adafactor, with momentum, exhibit robustness similar to ADAM and outperform SGD significantly. Our findings challenge the common belief that ADAM is the best optimizer, as no single algorithm emerged as the clear winner in terms of performance or hyperparameter stability. Following initial tests, we aim to identify the key components of these optimizers that contribute to their performance and stability. We examined simplified versions of these algorithms, such as Signum and Adalayer, to understand their impact on stability and performance. Our empirical study revealed that optimizers like Lion, Adafactor, and ADAM, except for SGD, show comparable performance and stability across different scales and transformer architecture variants. We also found that Signum and Adalayer can recover the stability and performance exhibited by ADAM. Through our investigations, we concluded that adaptivity is crucial for the last layer and layer norm parameters, while the remaining parameters can be effectively trained using SGD. Our work extends the comparison of optimizers beyond ADAM to include SGD, Lion, and Adafactor, considering various hyperparameters like momentum and weight decay. Section Summary. In this section, we empirically investigate the stability of various optimization algorithms, including SGD, ADAM, Lion, and Adafactor, across different hyperparameters and model scales. We find that, except for SGD, these optimizers exhibit comparable performance and hyperparameter stability, challenging the prevailing belief that ADAM is the superior optimizer. By studying simplified versions of these algorithms like Signum and Adalayer, we show that adaptivity is crucial only for specific network parameters, while the majority of parameters can be effectively trained with SGD. Section: Comparing optimizers across hyperparameters, architectures, and scale. In this section, we begin our experiments by using hyperparameters suggested by previous studies, such as setting beta_1 equals 0.9. We start by finding the best learning rate through a learning rate sweep for each algorithm. Once we determine the optimal learning rate, we then conduct sweeps for the other hyperparameters one at a time. However, this approach may overlook interactions between hyperparameters, especially in two-dimensional scenarios. Although exploring these interactions is crucial for future research, it was not feasible within our project's computational constraints. For instance, parameters like batch size and learning rate may exhibit 2D interactions. Despite this limitation, our one-dimensional sweeps offer a practical method to assess hyperparameter stability across various algorithms commonly used in practice. We train language models on C4 tokenized with the T5 tokenizer and evaluate the results based on validation loss. As mentioned earlier, we believe it is essential to evaluate algorithms based on both their performance with the best hyperparameters and their stability across different hyperparameter values. In this section, we present the outcomes of sweeps for the two most sensitive hyperparameters, learning rate and momentum, beta_1. We compare 5 algorithms: ADAM, Adafactor, Lion, Signum, and SGD. Additional analyses for weight decay, warm-up, beta_2, and epsilon for the 150 meters standard model can be found in the appendices. We utilize standard implementations of AtomW, SGDW, and Lion, along with a modified version of Adafactor that includes momentum. Signum is treated similarly to Lion due to their similarities in hyperparameter settings. While we experimented with the SOFIA optimizer, it did not outperform Signum, so we excluded it from further comparisons. Our models are based on the Olmo codebase and consist of decoder-only transformer models in 3 sizes: 150 meters, 300 meters, and 600 meters. These models vary in width, depth, MLP hidden dimension, activation function, positional encodings, attention heads, and training setup. We also consider 2 training variants to assess the impact of QK layer norm and Z-loss on model stability. For all models, we use a batch size of 256 and a sequence length of 512. We train the models for a specific number of steps corresponding to approximately 20 times the number of parameters. The training duration varies for different model sizes. We set default values for weight decay, learning rate schedule, beta_2, and epsilon. We then conduct learning rate sweeps, adjusting beta_1 for each algorithm accordingly. Our results show that most algorithms perform similarly at their optimal learning rates, with SGD being the exception due to lower performance and stability. Further analyses explore the impact of architecture choices and longer training times on stability and performance. Overall, Adafactor and Lion demonstrate competitiveness with Atom, while SGD lags behind in both performance and stability. Section Summary. In this section, we experiment with various optimizers by starting with recommended hyperparameters and conducting learning rate sweeps to find the best rates. We then perform one-dimensional sweeps for other hyperparameters, acknowledging the limitation of neglecting 2D interactions between them due to computational constraints. Despite this, our methodology provides valuable insights into hyperparameter stability across different algorithms commonly used in practice. Section Takeaway. In this section, we will explore the key factors that contribute to the stability and performance of optimizers. Our previous analyses showed that various optimizers perform similarly to Atom in terms of stability and performance. We aim to delve deeper into how preconditioning impacts the effectiveness of adaptive optimizers in achieving both stability and performance. Atom and its variants are known for their adaptivity at a granular level, adjusting learning rates for each parameter during training. This adaptivity is believed to be crucial for the stability and consistent performance of these optimizers. However, we want to understand to what extent this adaptivity is necessary for different network parameters. By breaking down the essential elements that ensure performance and stability, we aim to determine if simpler optimizers like SGD can achieve similar benefits with minimal changes. To ensure a fair comparison among all optimizers, we will set beta_1 equals 0.9 for each optimizer in this analysis. Our primary focus will be on studying a modified version of Atom called Adalayer, which operates at a layer-wise level. We chose Adalayer for this study because it offers a clearer understanding compared to the full Atom optimizer, helping us identify critical parts of the network that significantly impact optimizer performance and stability. It's important to note that this layer-wise approach is a specific instance of a previously known optimizer known as blockwise adaptive gradient with momentum, BAGM. Section Summary. Takeaway. Performance and stability with respect to learning rate and momentum are comparable across non-SGD algorithms within certain ranges. Other hyperparameters like weight decay and warm-up length have smaller impacts on stability and performance compared to learning rate and momentum adjustments. Signum and Atom show similar performance and stability for language modeling, especially when beta_1 equals beta_2, suggesting that the main advantage of Atom lies in the ability to independently adjust beta_2. By exploring a layer-wise variant of Atom called Adalayer, we aim to understand the role of adaptivity in achieving optimizer stability and performance across different network parameters. Section: Add a layer. In this section, we explore the behavior of adaptive optimizers like ADAM by introducing a layer-wise version called Add a layer. Add a layer, along with ADAM and Addifactor, stores information about the second moment matrix but with varying levels of detail. For a layer with dimensions m by n, ADAM maintains the second moment matrix explicitly using mn parameters in matrix form. Addifactor approximates the second moment matrix by storing row and column averages, while AddAlayer simplifies this further by storing just a single scalar as the average of the second moment matrix. We will later extend AddAlayer to average the second moment over a block of parameters instead of a whole layer. This modification is inspired by similar algorithms previously studied, but we focus on this variant due to its direct relation to ADAM and Addifactor. A simplified version of the AddAlayer optimizer is presented in an algorithm, with details like bias correction remaining consistent with ADAM. By examining the performance of AddAlayer across different learning rates, we observe that it outperforms SGD but falls short of ADAM in terms of both performance and stability across various learning rates. The key distinction between ADAM and AddAlayer lies in the preconditioning carried out by ADAM within a layer. This preconditioning is particularly impactful in layers where different weights exhibit varying gradient scales, such as the last layer in a model where tokens have different frequencies. To test the impact of this preconditioning, we introduce a corrected version of AddAlayer, denoted as AddAlayer *. This corrected version focuses on treating the weights feeding into a logit as a separate block. Our experiments show that AddAlayer * significantly improves performance and stability, almost matching ADAM's performance. By analyzing the effective learning rates used by AddAlayer * for different logits, we confirm that adapting the learning rates for different weights separately is crucial for enhancing performance and stability. Further investigations suggest that most layers, except the last one, only require a simple correction to their learning rates. We explore the possibility of training the remaining layers with SGD, supported by the observation that the learning rates assigned by AddAlayer * to these layers are quite similar. However, training only the last layer with AddAlayer * and the rest with SGD leads to improved performance but falls short of achieving the stability of AddAlayer * and ADAM. To address the instability observed in layer norm blocks, we incorporate layer norm parameters into the training process with AddAlayer *. This adjustment proves effective in restoring both performance and stability. Additionally, experiments with different model sizes and training strategies reveal insights into the impact of adaptivity in different layers, emphasizing the importance of tailored learning rate adjustments for optimal performance. Section Summary. In this section, we introduce AddAlayer, a layer-wise version of adaptive optimizers like ADAM, Addifactor, and AddAlayer that store diagonal second moment matrices with varying granularity. AddAlayer stores a single scalar as an average of the second moment matrix, and a modified version, AddAlayer, shows improved performance and stability by preconditioning weights in different logits separately. By freezing AddAlayer * learning rate scales at initialization for most layers except the last layer and layer norm, we can recover stability and performance, highlighting the importance of adaptivity in specific layers for optimal training outcomes. Section: Discussion and Limitations. In this section, we have extensively compared various optimizers for language modeling. We have observed that many optimizers show similar performance and stability in terms of hyperparameters. Upon closer examination, we have demonstrated that adaptive optimizers mainly benefit from how they handle the last layer and layer norm parameters. Our study has some limitations, such as only testing a few architecture decisions due to computational constraints, conducting one-dimensional hyperparameter sweeps, keeping batch size constant, and focusing solely on language modeling with one dataset. Despite these limitations, we believe our research provides valuable insights into optimization for language modeling, indicating that the choice of optimizer may not be the most effective way to enhance efficiency.